The Daniel K. Inouye Solar Telescope is the largest solar telescope ever built. With a whopping 4-meter diameter mirror, it reveals the sun at the highest resolution ever attained. It's currently finishing up construction and commissioning atop the 10,000-foot summit of Haleakala, Hawaii. When it commences science operations in 2022, DKIST will be capable of examining the sun in unprecedented detail, from its surface all the way out to its corona. And it joins NASA's Parker Solar Probe and ESA's Solar Orbiter just in time to catch the sun waking up from a decade-long quiet period. Welcome to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer, and there's a new big player on the solar telescope front. The Daniel K. Inouye Solar Telescope, or DKIST as the cool kids call it, is very much under construction. But even its early first light images reveal the sun's surface at a level of detail never seen before. Despite being stuck here on Earth, DKIST's resolution is higher than ESA's Solar Orbiter, which gets to within 1/3 Earth's distance from the sun. So today we're going to talk about how the world's largest telescope works and what it can tell us about our home star. But first, I'd like to thank Magellan TV, who are very kindly sponsoring today's video. Their documentary, called Set Course for the Heart of the Sun, tells the story of the Parker Solar Probe, which flies so close to the sun it actually passes through its atmosphere. You can enjoy this and many other documentaries on Magellan TV. It's a new streaming service that features topics on art, nature, history, and of course, space and science. And now Magellan TV is offering my viewers 30% off an annual subscription. That's a full year of Magellan for just $3.50 a month. And this offer applies to both new and returning subscribers alike. Simply visit the link in the description of this video to claim your discounted membership today. The sun's explosive behavior is driven by magnetic activity. Solar flares and coronal mass ejections can potentially damage satellites, disrupt communication networks, and knock out electrical grids. So, being able to predict solar storms well in advance means understanding the details of how the sun's magnetic field works, and that means monitoring small-scale changes on the sun to see how they develop over time. Much of the sun's extreme activity takes place in its outer atmosphere called the corona. Yeah, I've heard the joke before. Corona, good one. Even though it's high above the sun's surface, the temperature is actually millions of degrees hotter. And that doesn't make any sense. It's like raising your hand away from a hot stove and then it suddenly heats up and bursts into flames. So understanding how the sun's internal energy gets transported into the corona is one of the biggest questions we have about the sun, and by extension about stars in general. One idea is that energy gets carried up via twisted filaments called magnetic flux tubes. Of course, the sun's magnetic field is invisible, but it traps charged particles just like a bar magnet traps iron filings. And not only that, but the magnetic field polarizes the light that's emitted by those trapped particles. The stronger the magnetic field, the greater the polarization. So DKIST is designed to take images, spectra, and polarimetry of the sun all at the same time. And it can do it at a high enough cadence to actually watch the magnetic field change. The observatory is named after Daniel K. Inouye, the late senator from Hawaii. Its 4-meter primary mirror collects more than 6 times as much light as the previous record holder. It might seem a little strange to need such a large mirror to study the sun. I mean, after all, it's so bright you can even see it during the daytime. So what do we need a large mirror for? Well, the bigger the mirror, the higher the resolution, and therefore the smaller structures it can see. The magnetic flux tubes are thought to be less than 100 kilometers across. With a 4-meter mirror, DKIST can resolve features as small as 25 kilometers, so it should be able to spot them without much difficulty. A large mirror makes the telescope a lot more sensitive to light. Now that sounds really strange given that they're looking at the sun. Yes, the sun is very bright, but the sun's corona is very faint, and it can only be seen by artificially blocking the sun's disk. The bigger the mirror, the more photons it can collect to make out those fine coronal details. More photons collected quickly means more light for the cameras, which means short exposure times. And that allows DKIST to image the sun once every 5 seconds and build up a near real-time view. Instead of a traditional telescope design, DKIST uses an off-axis Gregorian optical design to eliminate any central obstruction that would otherwise scatter light, and this is especially important for observing the corona. The primary mirror is only 75 millimeters thick, and it's polished to an accuracy of less than 2 nanometers. In other words, if the mirror were scaled to the size of the continental United States, its largest imperfection would be less than the thickness of a dime. Since DKIST will observe the sun all day long, its mirror is supported by 120 actuators behind it and 24 additional actuators around its rim. And these actuators push against the thin mirror to prevent it from sagging as it moves throughout the day. But looking at the sun means that the mirror and the telescope gets very, very hot. Hot enough to damage the mirrors and render the telescope useless. So the primary mirror is actively cooled from behind with chilled air. The mirror sends the beam off to the secondary. But by this time, the beam's diameter has shrunk from 4 meters to less than 1 meter. And that means about 13 kilowatts of energy is bearing down on the secondary. And that's enough to pop a bag of popcorn in about 3 seconds. So, to protect the secondary from melting down, the light has to first pass through a heat stop. The heat stop is a donut-shaped pipe that's fed by large hoses that pump liquid coolant through it. The coolant carries away something like 90% of the heat energy. Now, if the heat stop were to suddenly fail, an emergency shield closes to disperse the light away from the secondary. But the shield can only do that for a few minutes before it disintegrates. So during that time, an emergency cover deploys over the primary mirror and the dome's aperture door closes. In fact, the entire dome is specifically designed to keep the telescope from overheating. It does this with a combination of a white paint job, shielded shutters, and it uses a single 4-meter circular aperture door instead of the traditional open slit. Now back inside, the beam enters into the heart of the observatory, the Coudet lab. This is where the science happens. The beam reaches the deformable mirror of the adaptive optics system. 1,600 actuators adjust the mirror's surface 2,000 times a second. This removes the atmospheric distortions from the light in real time and allows the telescope to see features as small as 25 kilometers across. The corrected beam can then be split to enter into multiple instruments. And this allows DKIST to image and take spectra of the sun at different wavelengths simultaneously. Different wavelengths of light correspond to different layers of the sun's atmosphere, so this technique allows a three-dimensional picture of the sun to emerge in real time. The entire lab rotates to follow the sun throughout the day and keep everything lined up in the instruments. Its rotation system is so precise it maintains the lab's position to an accuracy of just 3/10,000th of a degree. That's less than the thickness of a human hair. The entire lab is a clean room that keeps the dust levels down to just 1 part in 10,000. Clean rooms typically can do this by sealing off its doors, but the Coudet lab must let the light beam enter through the roof. Passing it through a glass window could introduce more distortions and would require regular cleaning. So instead, the Coudet lab uses an air knife that blows a continuous blade of air across the roof opening. The airflow is laminar, so there's no turbulence to distort the image. Speaking of which, its first light images are stunning, and they're a real teaser of what DKIST will deliver. These are the highest resolution images ever taken of the sun. It reveals structures as small as 30 kilometers across. The image shows a pattern of turbulent, boiling gas that covers the entire sun. These convection cells, called granules, are each about the size of Texas. Hot solar plasma rises in the bright centers of the granules, cools off, and then sinks below the surface in the dark lanes along the edges. Now, if you look along some of these dark lanes, you'll see that there are some tiny bright markers of magnetic fields. These bright specks are thought to channel energy up into the corona. In other words, they may be the long-sought magnetic flux tubes that heat the corona up. Now, this image was just meant as a test of the telescope's camera and optical system. It's not science quality, so nobody can draw any proper conclusions about what the bright spots actually are. But it covers an area of 36,500 by 36,500 kilometers of real estate, yet it reveals details as small as 30 kilometers across. That's actually about a factor of 10 smaller than ESA's solar orbiter will be able to see, even though it will close to within zero point 0.3 astronomical units. However, Solar Orbiter is also carrying a number of different instruments on board, including in situ experiments that can only be carried out near the Sun. And it can image the Sun at ultraviolet wavelengths and will eventually climb above the plane of Earth's orbit and give us our first glimpses of the Sun's poles. And then nothing will come closer to the Sun than Parker Solar Probe, which will fly through the Sun's corona at just 0.05 astronomical units. And then there's the Solar Dynamics Observatory, SOHO, and many others with their own unique capabilities. It's like they're the Avengers of heliophysics. In any event, the timing for all of this is actually pretty great because the Sun is starting to become active again. And that means we're going to start seeing more sunspots, flares, and coronal mass ejections as the Sun's magnetic field starts to tangle up. In fact, one of DKIST's early images was of this sunspot taken in January 2020. It really shows off the three-dimensional structure of the sunspot. The dark central region is where the magnetic field lines are so densely concentrated that they can open up a huge gap in the surrounding convection cells. And by huge, I mean about the size of the continental United States. But believe it or not, that's actually not really that huge for a sunspot. Many are actually the size of Earth, and some can grow to be even much, much larger. Now that the Sun is starting to get active again, we can watch the sunspots evolve in very fine detail. And this is going to help answer some long-held questions about our home star. Not the least of which is, why is its corona so hot? In fact, the Parker Solar Probe is getting closer to the Sun with each orbit, and it'll eventually get so close it will fly through the Sun's corona. But it's already made some surprising discoveries about the Sun's magnetic field, and even translated some of its measurements into sound. I made a video about that, so I'll tell you more about that and let you listen in to those sounds of the Sun in our next video. Thanks to my patrons for their generous support, and I'd like to welcome Pete Beck and Gita and Todd Vandermark. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friends.